to all of all. And on the behalf of Aeronautical Department and Parul University, sir, I welcome you for this webinar. Sir name is Dr. R.K. Sharma. Sir has done his graduation in BSc Honor from University of Delhi in 1968 in the Mathematics Department. And then after that, sir pursued MSc in the Mathematics from University of Delhi in 1970. After that, sir is very keen interested to do something for the nation. So he has done the PhD in the space dynamic from the University of Delhi in 1977. And sir started working as a junior research fellow at University of Delhi from September 1970, May 1973. After that, sir has worked in the applied mathematics division in the Vikram Sarabhai Space Center, Trivandrum, Kerala, as a scientist for 38 years. He has given the honor to be the head of the division since November 2004 to 30 June 2011. After that, sir has been retired from the ISRO, and then after that, sir has joined the Karunia Institute of Engineering and Technology as a professor. And from year 2011, he is working as a professor in the space dynamics. Sir has awarded for the mission in the ISRO in 2007 for GSLV F04 mission. And from 2012, sir has been awarded for the best researcher in the Karunia University till date. Sir also got 2 funded projects and many research. Over 75 plus research journals sir have published in the Renowned journal. So, sir, it is our honor to have you here. And thank you so much. In the short time you accept our proposal and came here to give the scenario of India in this space. Thank you, sir. You can proceed.
Thank you very much, Madam, for the nice introduction. And it is an honor for me to deliver a talk to the students, because that's what I joined the teaching after working in ISRO for 38 years, and before that 3 years full-time researcher in space dynamics area. So that is that only pushed me to teaching, and now I am completing almost 10 years now here in Karunia Institute of Technology and Sciences. So let me start the lecture now. So I talk a part of India has been doing, extremely well in the area of space since it joined in this area in early 60s, and gradually we have become a strong nation in this area. Indian Space Research Organization is the National Space Agency of the Republic of India, headquartered in Bangalore. Normally, departments are in Delhi, but it was in Bangalore because Professor Dhawan, when he, after the death of Dr. Sarabhai, because Sarabhai was in Ahmedabad, he was the director of the Physical Research Laboratory, and he used to visit from there, Trivandrum and other centers. So Professor Dhawan said he was the director of Indian Institute of Science. He says he will be there. He will not like to leave that, but he would be happy to head the Department of Space. So because Indian Institute of Science is in Bangalore, so our headquarters was shifted to Bangalore. It operates under Department of Space, which is directly overseen by the Prime Minister of India, while chairman of ISRO acts as executive of DOS as well. ISRO is the primary agency in India to perform tasks related to space-based applications, space exploration, and development of related technologies. It is one of the 6 government space agencies in the world which possess full launch capabilities, deploy cryogenic engines, launch extraterrestrial missions, and operate large fleet of artificial satellites. You can see right side the building of the. Originally, it was not in a. It did not had its own building, and gradually, the Department of Space it has in Bangalore has its own building, and called Antariksh, and this is Antariksh Bhavan, and then the Department of Space and ISRO headquarters in Bangalore, and this is the prime center, Vikram Sarabhai Space Center, Trivandrum, where I have spent 38 years. And you can see here the other building. I spent some time in this building. This is called main building, and then there is a building here where you can see that is called 9-story building. Probably that was the first 9-story building in Toronto. So I spent most balance of my career from 1985 to 2011 in that building. The Indian National Committee of Space Research in COSPAR was established by Government of India under the Department of Atomic Energy, DAE, in 1962 on the request of Dr. Vikram Sarabhai, reorganizing the need in space research. INCOSPAR grew and became ISRO in 1969 within DAE. In 72, the Government of India had set up a space commission and the Department of Space, DOS, bringing ISRO under the DOS. The establishment of ISRO under the institutionalized space research activities in India. It since then has been managed by the DOS, which governs various other institutions in India in domain of astronomy and space technology. ISRO was the world's first space agency to find water on the moon when Chandrayaan 1 was put into moon's orbit. It had identified the water there and insert a probe in orbit of Mars in its maiden attempt. All other people who tried Mars mission in their first attempt, they didn't do. They did in later, but the ISRO was able to do in the first attempt. It has the world's largest constellation of remote sensing satellites, because that is a strength for us. Our country is large and we need these remote sensing satellites, and that is how our space program started with, to help the human beings of our country as well as to other part of the world also. So you can say Indian Space Organization, these are the important centers. Vikram Sarabhai Space Center, that is the where all launch vehicles are developed, are all researched here, and they are then Liquid Propulsion System Center, LPSC. Here, all the liquid, because liquid technology, liquid rockets are very important, and so this is a separate center. And Satish Dhawan Space, where they launched Satish Dhawan Space Center. Professor Satish Dhawan, after his passing away, then this center was named as Satish Dhawan Space Center, Chirerikota. And then here all launches take place. And UR Rao Satellite Center. So after the death of because Professor Rao did wonderful job for the satellite technology, and this center was located in Bangalore, and it was very near to NAL. Originally it was in Peenya, but gradually NAL had given some part of the land, and then there this satellite center started, and now it has got, of course, some more branches over there. And so this is now called UR Rao Satellite. So all satellite building etc. takes place here. And space application, all space application related things are done at Ahmedabad, SAC, Space Application Center, Ahmedabad. And remote sensing, all the images which come from the satellites, they are all analyzed here in Hyderabad. National Remote Sensing Satellite. These are all the important centers. ISRO inertial, see the inertial unit, these are all very important. So this is still called a unit, but of course this plays a very important role. And this is there in Trivandrum. and master control facility MCF. They all geostationary satellites. They are. This is at it is at in Hassan in Karnataka. So it is there around 200 kilometers from Bangalore. So these are all the important ones. So branches of ISRO. So these are all, you see, some of them which are already I told you, Vikram Sarabhai Space Center, and these things I have already told you, and then some more are over written there. Antrix Corporation Limited, because some of the business oriented things are handled by Antrix Corporation. And then semiconductor laboratory. This is at Chandigarh. This is also playing important role. And in Northeast Space Application Center is also there at Guwahati. Master controls. We have two. One at a similar thing in Bhopal also was made in Hassan as well as in Bhopal, and remote atmospheric research laboratory (NRL). So like that, you see, it has grown quite a lot. And then you can see here in this figure India's map, and you can see where are our various where are the various units of ISRO centers. See the Chandigarh, this in Chandigarh, and this is Dehradun. Dehradun, we have Indian Institute of Remote Sensing. So here training is also given, and courses are taught here. Center for Space Science and Technology. New Delhi, we have the DOS branch secretary. Main is there in Bangalore. And Lucknow, we have a STRAC. See, tracking center. Here we have a tracking ground station. See, the tracking stations are located in such a fashion that the satellites are, when they are put into orbit, they are tracked. They have to be their path has to be found, and so this has been planned long time back, and it is there. It is existing there. And even you can see Andaman Loco. Here also we have Downrange Station here, Port Blair, Andaman Islands. Tirupati, we have National Atmospheric Research Laboratory. So you see, you can see it's such a huge growth has taken place. When started with a very small thing, I will touch upon how with a small thing it is started. And in Bangalore and in Trivandrum, there are more activities. See, Bangalore, you can see this much area, so many units and center. These things are there in Bangalore. And this is Hassan. This is Bairalu. This is a deep space network has been put over here. It's very important, very expensive. This facility was developed with a lot of expenses. And Alua, we have ammonium perchlorate, for solid propellants. This was necessary. Then he was our director at that time. I was there, Professor Gavarikar, and he said, we must make this as a separate unit. Otherwise, we cannot sustain the requirements. So this was done, ammonium perchlorate, because this is required as one of the propellants there for the solid. And solid propellants play a very important role in our launch vehicles. That you will see. I will touch upon those things. Mahendragiri again, we have the all facilities, cryogenic, liquid propulsion here. All testing facilities are there. Mahendragiri, Tamil Nadu. So in Trivandrum, we have got Vikram Sarabhai Space Center, Liquid Propulsion System Center. It is slightly away from this. That is Valiamala. That area is called Valiamala, nearly 40 kilometers from Trivandrum. And ISRO Inertial System Unit, and Indian Institute of, and then the Space Department started Indian Institute of Space Science and Technology. Originally, the students they were taken from the IIT entrance, and then they were joining there, and then later on they had their own exam, and so doing very well. The students coming out from this, they are doing very well in the area of the. So you can see how much is the growth of the Space Department. India's first rocket launch became possible quite literally after divine intervention. The land which now houses India's famous Vikram Sarabhai Center, from where in 1963 Indians watched their first rocket head for space, was originally a Catholic church. It was a Catholic church. St. Mary Magdalene Church is located near Earth's magnetic equator. You see, because Dr. Sarabhai was a astrophysicist, and for him magnetic equator had meaning, and he was an experimentalist also. So that he said, somehow we must do something here. This had stirred Dr. Sarabhai's interest. He went to speak to the bishop, Dr. Peter Bernard Pereira, about getting the church. The bishop gave it gladly after consulting for the great mission of space research. by India. So TULS, this is the one where internationally, Tumba Equatorial Rocket Launching Station in 1963. The Tumba Equatorial Rocket Launching Station is located in Tumba, Trivandrum, is very close to Earth's magnetic equator. It is currently used by ISRO for launching sounding rockets. It was open. It is was opened for other agencies also to test their French people used to come, and other countries people used to also come to test there, because near the magnetic equator, the upper atmospheric conditions are different. So it is currently used by ISRO for launching sounding rockets. These rockets are designed to take instruments and perform scientific experiments during the suborbital flight, because these are all suborbital flight. November 21, 1963 marked India's first venture into space with the launching of two-stage Nike Apache sounding rocket from TULS. So this was the day when the whole country enjoyed that we are also able to do a two-stage sounding rocket. So this is the church, friends. This is the church, and now it has become wonderful museum, space museum. It is one of the best museum. People say, yeah, of course we have seen number of times, but those who come, even when my guide, he visited there, he says it's excellent, because he might have seen elsewhere also in different countries also. And then he said, this is these are full scale models for PSLV, and this is for ASLV. So these are all full scale models they have been. And so many lakhs of people might have visited this museum till now. Students come in bulk there. And you see, this is the initial history where all these, some of these are top scientists at that time. Maybe in this Kalam also must be there somewhere. Dr. Kalam also must be in this. And you see, one of our very senior scientists at that time, these are the means, because the money, no money, because the autonomous body at that time, no government, little funding only. On cycle, he is carrying the payload. This is the payload, which that sounding rocket will go, and he is going on that. So that was even a chief was not there. You see here, you can see Dr. Kalam is this, because it may be difficult to recognize. He is so young, and then this picture is also not, so it's a very old picture. But these are all 5 very, very strong people of space. Here, Dr. Armamundan, he became later the director of the satellite center. You are now called, earlier it was satellite center, Service Satellite Center. So he became the director there, and he was in Trivandrum for a long time. And Dr. Kalam, and there was Murthy, he was at that time the director. And this was they are all, these are Mr. Ishwar Das, he was mechanical expert and handling a very big mechanical facilities. He was the deputy director for that. And he was also Vijay Rao. He developed later on the Sriharikota. From there, he was shifted to there, and then he developed the entire Sriharikota. Sriharikota was a island, and developing that was not an easy task. That gigantic work was carried out by him. Now, these are the launch vehicles. We started with this launch vehicle. This is all four solid. With solid only we had. And you see, friends, this propellant technology nobody gives. So this is all secret for all countries. Nobody gives you just like that. So we were good in solid propellant. So we have developed some of the propellant. So this is a 4-stage. And even with 4-stage, it was not able to carry much payload. Then from there, we jumped to ASLV, then to PSLV, then to GSLV, Mark 1 and Mark 2, and then to this. And this is the one where we are planning to send human beings also in space. This is the photo of the Vikram Sarabhai Space Center. I thought once more. And this is the bust of Dr. Sarabhai. Sarabhai's thing he was put, because this is the center, where he had uh, mm, started his, I mean, this thing. Originally, it was not called Vikram Sarabhai Space Center. It was called Space Science and Technology Center. But later on, after he died at a very young age. Just he was 51-year-old only, and they are only in Trivandrum in Kovalam Hotel, 5-star hotel. Night he slept and he didn't get up. So probably a massive heart attack. So, but the path which he has shown to the people and the people whom he trained, they did wonderful job, and then we have reached to such a heights in the space area. You see, this is the thing. Dr. Kalam was the project director. This was the first project, SLV3, and Professor Dhawan later, after Dr. Sarabhai's death, Professor Satish Dhawan took the chairmanship, and then he was made the project director. And these are the the SLV, along around 17 tons weight. And you see, first launch unfortunately failed by Yemen. In the first flight, a jammed valve in the control system of the second stage led to the failure. I was there in the Sririkota because I was specialist in calculation of the orbital lifetime and some other calculations also. So this took a turn, because the valve jammed it over. So once it opens and the propellant going, so it is giving a the requires force. Then it is taking and it's not closing. The control system need to give only required, what is needed, but it didn't do that. It could not close, and that's how that thing. It was not a great failure, but well, in rocket technology, even a simple thing, a very small failure is a failure, and entire mission it becomes waste. So this became, but then on this we had a wonderful later after this. When this failed, Dr. Kalam, because he worked very hard and his other people worked very hard, he was feeling very sad. But then Professor Dhawan said, he had addressed us in Vikram Sarabhai Space Center, and he said, see, all the responsibility of the failure I take. The entire blame I take. And when this became a grand success, then he says the entire thing goes to Dr. Kalam and his team and the all people who worked in Vikram Sarabhai Space Center. See, that's the quality of a leader, great leader. So Sarabhai was a great leader, and then so was Dr. Kalam. Where he has reached. From there he went. He worked for launch vehicles, then to missiles, and then he went there, and then finally he became the president of this country and got all the awards, including the Bharat Ratna. So, see, that is the kind of thing. And we were very lucky that we worked under his close mentorship for a couple of years. I was there almost 9 to 10 years. So, because I joined in 1973, and immediately this project was going on, so we were immediately pushed to work for this. Even then we were in different divisions, but well, everybody was working for this vehicle because we have to make this a success. So this became a success, and later on these also became success, and so this mission anyway was closed. And then we started with the ASLV mission. The problem happened in this mission, the first two failed. The reason was the enough wind tunnel. You see, wind tunnel also you must be familiar. Wind tunnel, enough tests were not done. So the actual characteristics of the vehicle when it goes in upper atmosphere were not fully studied with the help of wind tunnel. The wind tunnel gives you realistic things, and in those days, even this CFD and other things also was not because computers were also not so powerful, so that even CFD results were also, now we have computational fluid dynamics results and other results, Navier-Stokes equation you can solve, a lot of things you can do, but at that time they were, so this went away and it had got into problems, and that's why these missions failed. But then after study, then there was a national failure committees, etc. Then these failures were analyzed, and finally these missions were successful. They were successful, and then this mission also, because this mission was not of great, because around 150 kg weights are not very useful, because SLV 3 was only for us to show. The main aim for SLV was to put a satellite of 440 kg so that it is 100 days in life. But these were not so attractive, so we had gone to the PSLV. PSLV has been doing wonderful job, except for some minor errors we got committed. We are committed. Otherwise, it is a almost 100% success, and it has got various. It has been tested various. When this team was made by at that time, the young people, young bright people were put in PSLV. Young, those who are young, because they knew that it will take some time, so that the people, those who are young, they will reach at the age when they will be the best, suitable for this. So people had lot of, people who worked in this, genius worked this, they became leaders, great leaders. A lot of got the directorships and other higher positions as well. So these are all, the various. It's different. You can see base. This is the base. There are 6. These are called strap-ons. So here you have 6 strap-ons and core alone vehicle, no strap-ons. So this is called a PSLV-CA, and this is Excel. Here, when Moon mission was to go, Chandrayaan-1 was to go, then they needed some more, payload capabilities that it should be able to carry. So they extended this wherever possible, so that payload goes more. So this was extended to that. You can see that some more payload, some more extensions were made. And then this is HP, Excel with high performance PS4. PS4 is the upper stage, 4th stage, which is a liquid. Two twin engines are there, and they give very precise. These are wonderful. They have performed over the years. When I say wonderful, over the so many, now 53 launches PSLV has already gone. And this is the PSLV's 3S. PS2 plus strap-on removed. Strap-ons are removed. So strap-ons are removed. So PS3, HPS3 and PS4. So like that, different things work. So you can see that how nicely our young engineers had developed this entirely developed by our young engineers. No copying here and there. This is the 50th mission, when they were celebrating their 50th mission of PSLV. And PSLV Polar Satellite Launch Vehicle, I give you some idea about this. PSLV has unique configuration of alternating solid and liquid. No other country uses this kind of configuration. The first stage is a large solid motor, augmented by 6 solid PSLV strap-on motors. You have seen the strap-ons. So, and then second stage has liquid engine burning N2O4 and UTMH. That is where we needed that ammonium chlorate, and those things go in first stage. The third stage is a solid motor. It has polyamide fiber, and this also are done in our replace. There is called replace. So these are all motors are also built there with the help of fiber, so that weight is decreased and but the strength is maintained. The fourth stage is used as the terminal stage to provide precision injection. So this does wonders, because finally we need very accurate injection. And many of the mission, it so happened, because still, though even then it does very accurate injection, but still we have to keep some fuel in the satellite system so that it can be corrected, orbit can be corrected. But most of the time that fuel remains just like that, because this goes as it is perfectly well. This stage is powered by 2 identical pressure-fed engines using monomethyl hydrogen, MMH, and MON3, 3% nitric acid and 97% nitric tetroxide as propellant. And now you can see size 44 meter, diameter 2.8. The mass is nearly 294 tons, 4 stages. The other one is not counted, otherwise it becomes 5. propellant capabilities. Payload in low Earth orbit, we can send 3,250 kg. Later on, with some improvement, etc., it can even go. And in sun synchronous orbits, because sun synchronous orbits, I will give you some idea about sun synchronous orbits. Since it comes from the orbit area, 1,600 kg, and this was used important to us. And payload in GTO. So this mission, this vehicle has been used for the geotransfer orbit as well. So that means geostationary orbits also, because for some time our GSLV was not fully ready, so we had to use this. Also was used for some missions. Now PSLV launches, you can see this. These are the latest launch was, even in this tough time of Corona, we have been able, our engineers are able to do these missions. These 3 missions they are able to do. This was anyway at that time things were okay, so this was done, and then 50th launch, then 51st, and these are all done during that period. And this this thing I have explained there. PSLV DL means variant has only 2 strap-on boosters with 12-ton propellant load on them. DL, 2 strap-ons on boosters instead of 6, only 2 strap-ons. And PSLV QL, this is QL here. A variant has 4 ground lit strap-ons instead of 6. It has got 4, each with 12 tons of propellant. And PXXL is the upgraded version of Polar Satellite Launch Vehicle in its standard configuration, boosted by more powerful stressed strap-on boosters, 12-ton propellant. Because when moon mission Chandrayaan-1 was to be sent, this requirement was there. Then research was done to improve upon this, and that was successful. PSLV 37 successfully, you see that time big news was there, successfully launched 104 satellites. See, the separation of these satellites also was the all theory is done where I was the head of the applied mathematics division, and my colleagues used to do the separations. 104 satellites in a single flight. In its 39th flight, PSLV C-37, 38th consecutively successfully mission. 38th consecutively successful mission. It launched its 714 Cartosat 2 series satellite. Cartosat, very accurate, very accurate images are derived from there, along with 103 co-passenger satellites on February 15, 2017. 2 more ISRO nano satellites, INS-1 weighing 8.4 and INS-2 weighing 9.7 were technology demonstration satellites from India. The total weight of the satellite was 1378. As I told you that is the kind of this thing it to use. But the news was 104 satellites, and their separation is the challenge, because you have to first thing you put how you put them there inside that small area, and then how you are going to separate them once they are in space. So all that studies were done by my colleagues. They were doing they worked very hard to do. They used to do. Of course, I was not there at that time, but before that also, when I was there till June 11, these studies were done, and I discussed with the person who did it, Mr. Negi, and he says, sir, it was a difficult thing, and once I visited there, and he showed me how difficult that study was. And you can see here this something I must tell you about this thing. Even then, everything moves in space. Sun is moving, Earth is moving around Sun, and Sun and the whole galaxies are moving. Everything, but still we have a fixed coordinate system. How it is fixed coordinate system is that with respect to stars, we are able to generate that. And when we say in a simple language, when sun comes on Earth equator, if sun comes on Earth equator, we call this as a vernal equinox. This comes either 20th or 21st of March in this turn, and it will be other side also. It comes from here, from south to north, and from north to south it will be on 22nd or 23rd. So this will be ascending node, and other will be descending node. So this is our x-axis. Center is the Earth center of the Earth, or center is the our origin, and z-axis is your pole of the Earth, and then this makes a right-handed coordinate system, and this is a fixed coordinate system. So in this fixed coordinate system, even then there will be small corrections needed because of various other factors, but essentially this is fixed with respect to stars. And such systems also, this vernal equinox, we can with respect to sun also we can define, or with respect to planets also we can define. So all our satellite orbits, when they come, these are the parameters, orbital parameters. You have, supposing, position velocity. The position velocity at any time they will change. From even in 1 second or even in half second, they will change appreciably, because the velocity of the satellite will be minimum 7.5 kilometer per second. So, but these parameters, the right ascension of ascending node, how it comes, if this is the orbit, this is x-axis, y-axis, this is Earth's equator, and where it cuts, this orbit cuts this Earth's equatorial plane or xy plane, that this angle between the x-axis and this is the capital right ascension of ascending node, and where is the perigee, the minimum distance from where you have the minimum distance, that will be, this angle will be in this orbital plane, small omega, and true anomaly is this theta is the true anomaly, and true anomaly is measured from the focus. This is the focus. If you are in an elliptic orbit, the center of the Earth will be focus. That is from the Newton's Kepler's laws. You can see that. And then you have defined this, and this is the inclination, with the angle between this plane and this plane, and this same angle will be here, because this and this is perpendicular. This is angular momentum vector. So my interest is to tell you this omega, capital omega. What happens is, when Earth is spherical, these will not change, but when Earth is oblate, we know there is a difference of 22 kilometer between Earth's equatorial plane and the polar equatorial radius and the polar radius, around 22 kilometer, 21.6. So that makes difference over secular effect. Secular means they are all the time increasing or decreasing. So capital omega and small omega, argument of perigee, and this right ascension, they have secular effect, as well as the mean anomaly also, or mean motion, you can say. So these three parameters have secular motion, and your sun synchronous orbits are defined with respect to this. How they are defined? These are defined like this. Sun synchronous orbits. Sun synchronous orbits are orbits with the secular rate of the right ascension of ascending node equal to the right ascension of the mean sun. See, sun will move up about 1 degree, less than 1 degree. That means it goes 360 degrees in 365.25 days. So if you divide 360 by 365 by 25 days, this many degrees per day. So this number, this will be the change due to oblateness. This J2 is called the oblateness coefficient, zonal harmonic J2. So this will be the effect, the rate of change of the capital omega. This must be equal to this. Now this is degree per day. When you want to convert, suppose you want to calculate I watt angle. If you are given this mean motion n, and you can calculate from Kepler's third law. So if semi-major axis is given to you, then you can calculate mean motion, and P is nothing but A into 1 minus E square. So if you know the orbit, elliptic orbit, general elliptic orbit we are taking, and then you can calculate the inclination I. This is degree per day, this is in radians. So you convert this also radians per second. Day you convert in second, degree you convert in radians, and then you can calculate I. So, and since this is minus, okay, and this is plus, to make this plus, this angle must be in second quadrant, because otherwise you cannot have a plus thing equal to minus thing. So cos I should give you a minus value. That gives only when I is in the second quadrant, because cos is negative in the second quadrant. So that negative, so all sun synchronous orbits are more than their inclination are more than 90 degrees. And because they are more than 90 degrees, we have to do, and our Sriharikota is around 13 degree latitude. So we have to do a lot of yawing. Pitch and yawing, pitch yawing we have to do to make the angle somewhere around 98, 99 degree, or it depends. Now, we can always find, if you are given your the orbit, if it is a circular orbit, you are given your altitude, then you can calculate this parameter P is 0, you can calculate, and then you can calculate the I, and then you can so a lot of yawing is done, and that is why in sun synchronous orbit, the payload capability is reduced, because we have to safeguard. Another thing in launching is we cannot take our launch vehicle. No stage should fall less than 200 kilometer from their mass where the area where people are living, from their land masses. So so that means 200 kilometer away it has to go. So these trajectories are designed in such a fashion, because when we take from Sriharikota, we have to see, if I show you in that, I have not put a figure, I have to go quite far away. I don't want to go. So you have to see that side, Indonesia and other countries, you have to safeguard them. And if in 98, when we take air, even Sri Lanka, we have to safeguard Sri Lanka also. So that has to done, and that is how, doing in all that, we lose some of the payload. So now I hope you understood sun synchronous orbits are orbits with the secular rate of right ascension of ascending node equal to the right ascension of the mean sun. And this is the mean sun. Sun also will have a small changes, but this is the mean value. For the satellite orbit to be sun synchronous, the inclination, semi-major, and eccentricity must satisfy this relation. And because this is plus, this is minus, I must be in the second quadrant. Now you can see some of the pictures taken. First day image of Cartosat 2. So these are all the satellites which are launched. You can see this is BKC block and Mithi River, Mumbai. This figure, see from the satellite, this is the image. So nice, so it looks so good. One can see easily the river also here. The people who are from Bombay, they can easily identify the thing. I do not belong from there, so but the people who are away, from there, they may be able to appreciate this more. This is first day image of Cartosat 2 series, part of Busto Arsio, Italy. See how cute, how nicely from space it has come. Acquired on 18/2/17. So you see the satellite does wonders. And otherwise, how do you take this picture? Because even if you take from a spacecraft, you will get only a part of this, but only from space such things are possible. This is part of Indore, Holkar Stadium. It is written here. So this is part of it. This is acquired on 15/1/18. I have little bit put more bigger, so it has become little bit this thing. But this is the figure. Cartosat series 2 series. Cartosat gives good figures. And this is again very nice. Cartosat 3. So some more improvement is there. ISRO high resolution, panchromatic calibration validation. Doha, Qatar. This is Doha, Qatar. This is there. Oversized vehicle training. And parking lane. This is parking lane markers also. As you can see, some markers also from space. Oversized reverse area. This is reverse area. This line is put here. And then observation tower. So this is observation tower also one can see. Road traffic. Road traffic also you can see here. So whatever. So nicely, from space we are able to see. This is the Haridwar station during this Kumbh Mela. I think this was taken. Roadways, bus stand, this thing, and then railway station, December 20th. Yeah, so this is during Kumbh Mela they have taken this. So this is Cartosat 3. And this is Cartosat 2 satellite helped nail the targets for India surgical strike. When India had surgical strike, so these were analyzed. This is one thing which is in public domain. There may be many good pictures which the ISRO will not give in public domain. Whatever figure I have taken all from public domain. So they are all available in internet. But just to tell you, so they would have they would have been studied very carefully which are the places, their hideouts, and what are the things, all those things, and then only they, with all that careful thing, they must have planned their surgical strike. Then only the result was excellent. The space capsule recovery. This was another very interesting study. The development which was done. Experiment SRE-1 is an Indian experiment spacecraft which was launched on January 10, 2007 from Sriharikota. In preparation for its re-entry, SRE-1 was put into an elliptic orbit with a perigee means the nearest distance from Earth surface, and apogee 639 kilometers. So this is the nearest from Earth's surface, and this is the farthest. It remained in orbit for 12 days before re-entering the Earth's atmosphere and smashing down into Bay of Bengal. So this was planned in this fashion with a velocity of 12 meters. See, it was finally reduced to 12 meters per second on 22nd January 2007. You see here, we were doing because we were posted in Bangalore at that time, because what has happened is at the same time the Chinese have done their ASAT. They had killed their satellite, and that has done lot of fragments, lot of debris. So the debris, I was in the area, specialized in this area of calculation of the hit probability of from the debris. So that so we were me and my other colleagues were there in Bangalore and calculating them during the night also. At that time, not many, those whatever were available, normally, as well as some of the Chinese, fragments that whatever those which US their system, the aircraft, the US Air Force, they take this responsibility of command. So they do all these. So we were doing with all that, and we found that some of the Chinese fragments were coming very near to our this satellite. So we are lucky that none of them. Once it was so much near that we had to tell the project director. Then he says, "Well, we have to take a risk, because doing at a short notice the change in the orbit is also not an easy task." But it was not very, but it came very close. So these are all. CSLV, another thing which afterwards, because the PSLV was not sufficient, we had to put gradually to geostationary orbits, that is 36,000 kilometers with the inclination 0. Then this project was initiated, and then Russia in the beginning agreed to give us the cryogenic upper stage. Some engines they gave us, and this GSLV is 49 meters tall and weight 414 tons. It is 3-stage vehicle. Now PSLV was 4 and it is only 3-stage, because that is the advantage of cryogenics. The first stage comprised a core motor of 138 tons of solid propellant and 4 stages of motor, each of 40 ton hyperbolic space propellant UH-25 and 2O. And second stage is now again liquid propellant. And third is a cryogenic, 12.5 ton of liquid oxygen and liquid hydrogen is there. aluminum alloy GSLV. Payload fairing was 3.4 meter in diameter and 7.8 meter long. Now these are the essentially PSLV, GSLV. You can see 44, 49, 4, 3, 320 tons, and this is 400. So from here we reached, because this was increased later. Originally it was 294. Later on, in extended mission, it got increased to this. And wherever it was possible, to enhance its capabilities. So this was, and then this is how it was. First flight was over here, and then it was over here. So this is how these are the so PSLV can take this many kg of payload to sun synchronous orbits to 600 kilometer. GSLV can place up to 5,000 in low Earth orbit and 2,000 kg. I think this is some mistake is there here. Kg to GTO must be 10 is more put more 2,500 to GTO. So this is, you see why I have put this is, you see this height is very low. It goes for a long time. It goes for a long time in a low altitude. Altitude, you see, altitude strap on, and then this altitude remains. And even and only it increases. So remains here, for a long time. It remains here. Only velocity, see, this is the velocity, and then it increases on the upper stage ignition. The ignition takes place here. The velocity was 4.9 kilometer per second. Okay, then you see this cryogenic, how much it increases. The balance has taken this, and this increases. Then suddenly this increases the whole thing. And finally, this is typically, I just wanted to show you that the trajectory of this is very typical. And sometimes it is during coast also. It remains for some time, it goes. And you can see here the velocity. This was this velocity to this velocity, second stage, separation, ignition. And you see here that there's not much increase. Now this is Mark III, which is the, you can say, which does a lot of good things, and which will be used for human program also. It is entirely done by our people, and cryogenics also. There it was, the height is 43, almost same height, diameter 4 meter, the diameter, and mass is, you see, mass is 640 ton, okay, and 3 stages. Payload to low Earth 8,000 kg it can, and this 600. If you go to human mission, it 400, so this may go to 10,000 kilometers, and G2 also it goes to 400. So the all larger our geostationary satellites missions, they are met with this. This booster 200 S200, 2 boosters are there. See, the 2 boosters are there, and this length is 25 and diameter. So this is entirely done by our engineers. And then solid, as to you can see, this is the thrust specific impulse is solid, burning time, and then core. This is the liquid, that core engine, 17 meter, and this is 2 Vikas engine. What we were using, whatever we used earlier, the two are clubbed together. Test, and this propellant mass and thrust and specific impulse for this is a liquid one, so 293, and burning time, UDMH, and this. So you see how nicely this simple made, and but made so strong. And this is also done by our engineer. That was the great thing. It took some time, but finally, our engineers have been successful. Length, diameter, propellant mass, and this is one engine which is developed by our people. No import, and specific impulse is 443. You see, 293 liquid to this is 443 cryogenics. So that's the great thing. And burning time is this. And during that, the velocity increases appreciably. Liquid oxygen and liquid hydrogen. This is oxidizer, this is the fuel. So you can see the pictures taken from geostationary, our inset thing. This is a colored one. When they do it, they do a lot of the research in the area of remote sensing at Hyderabad, and this is again a picture of this thing. And then you see here, these are all we cannot put our satellites in this geostationary, which is around 36,900 kilometer altitude from surface of the earth. These are all assigned by the international agency. So we have these areas, some frequency. Otherwise, they will interfere. You cannot put two satellites nearby also. So this is just to tell you that these are not at will that some other fellow come and he puts it over here. No, cannot. So these are all typically. Other countries also will be assigned to those who are there. They have to request them that they are putting a geostationary satellite, and then they have the latitude, because this in the longitude. Latitude is 0 because this is in the equatorial plane, Earth's equatorial plane. And these are all the type of systems, navigation satellites. So IRNSS, this does fixation of location of any place on Earth's surface in terms of its precise latitude and longitude. This system also, navigation satellites, our people have done a good job. INSAT and GSAT, weather study and predict weather satellites, these are all like this. And IRS, we have the largest fleet. Study of forest, desert, ocean, polar ice, and Earth's surface. This is done Earth's observation. And Chandrayaan-1, this is you see, we don't go in just one round. We go gradually in elliptic, and then every time we come over the near to Earth, then we give one more push here, one more velocity is added, and that is called Hohmann transfer. I mean, essentially, when you put it, when we used to go to another place, we define in that fashion. But this is, we don't essentially call it here, but we get into elliptic orbit, and finally we reach to the sphere of influence of this. And you can see over here, this, because time is less, I will just quickly show you the thing. This is essentially a trajectory which we do. We first put it into elliptic, and then finally we get into a orbit which towards the moon. And midterm, some corrections, etc. are done. Lunar transfer trajectory, and this is lunar capture around 1,000 kilometer, and then from 1,000 kilometer, then it is gradually brought to using that Hohmann transfer thing to a 100 kilometer circular orbit. Normally, most of the people are using 100 kilometer circular orbit. One advantage of 100 kilometer circular orbit is that with the time, the moon doesn't have an atmosphere, but moon's surface is not like Earth's surface. It has got a lot of mountains and other things. So and some mass things are there, mass concentrations are there. So gravity itself makes a circular orbit as elliptic orbit, and gradually, if 100 kilometer is there, with the time it may hit, it becomes highly elliptic, and the perihelion that is called, it will hit the surface and its life will end. That's why 100 kilometer probably people have found. And this is the picture taken from this one on 29th by that Chandrayaan-1. This is a picture of the Earth taken on 25th March 2009. And this is again by Chandrayaan-1 moon mineralogy mapper. See, nice, beautiful pictures they have taken. This is blue, water absorption strength on infrared. So a lot of this once you have these pictures, then a lot of research can be carried out by the people who are working in these areas. And this is Chandrayaan 3D view of moon. This crater depth is 400 meter. 400 meter, is the depth of this crater. This picture is also taken by our Chandrayaan. And this is Chandrayaan 2. Chandrayaan 2, unfortunately, in the end had some problem, but still a lot of things were our success only. We had the orbiter and other things. So this is the path, how this goes, and then finally how this goes around this, and then we take it. And we start, it will be here, and then by the time we could take it, this moon will be reaching here. So this is the path shown. The Chandrayaan 2 mission was a highly complex mission which represented a significant technological leap compared to previous mission of ISRO, which brought together an orbiter, lander, and rover. To explore the unexplored, we were planning south pole of the moon. The orbiter was placed in its intended orbit around the moon and shall enrich our understanding of moon, because it is there. Moon's evolution and mapping of the minerals and water molecules in polar region. using its 8 state-of-art scientific instruments. The orbiter camera is the highest resolution camera, 0.3 meter resolution. It's very, zero point 0.3 is 30 centimeter in any lunar mission so far, and shall provide high resolution images. It has been providing, which will be immensely useful to the global scientific community. The precise launch and mission management has ensured a long life of almost 7 years compared to planned 1 year. For the orbiter, orbiter will be for around 7 years. The Vikram lander followed a planned lander trajectory from its orbit of 35 km to just below 2 km above the surface. All the systems and sensors of the lander functioned excellently until this point and proved many new technologies such as variable thrust propulsion technology used in the lander. The success criteria was defined for each and every phase of the mission, and till date 95% of the mission objectives were accomplished and will continue contribute to lunar science. So only in the end, after 2 kilometers only, it got into problem. The signals did not got the signals, and finally it has hit the moon surface. So this is, Chandrayaan 2 NASA releases site of Vikram landing site, where, so this is somewhere it was there, because it is in that picture. It is it was identified also, where I was unable to now due to shortage of time I was not able to give you that thing, but this is the thing which they have identified. And pictures of moon surface from Chandrayaan 2. These are Chandrayaan 2 has taken this picture from its orbiter. These pictures. So like that, there will be thousands of pictures it will be releasing. And see, what happens is, another thing is, the moon's gravity, like Earth gravity, we know quite good way, but moon's gravity is still a model, is still to be improved, because this side, what we see only one side. It takes nearly 28 days to take a round around Earth, and it takes same time to take about its orbit, about its rotation, about its axis. So we don't see the other side of the moon, but other side of the moon is far different than this side. Its gravity models are still not very accurate. So all these data, gradually with time, when people will put effort, those who have very strong mathematical base, physics base, etc., and especially mathematics equations are to be solved. There. A lot of complicated calculations are there, and you need sophisticated computers also to solve them. Then only the good gravity models with a lot of data will emerge. And this is the Mars mission which India did on C-25 mission. And these are all the things which over the Mars mission are pushed in this. The trajectory is given here. I will show you the trajectory. See, what happens is, Mars is outside Earth orbit. So the velocity of Mars will be less than that of Earth. So when this starts, and what happens is, that is called Hohmann transfer. When this starts, Mars has to be somewhere on ahead, and this angle, when you join center of the sun to this will be around 43 degree. This angle, join Earth to sun and to the Mars, is around 43.4 degree or so. And this is called Hohmann transfer. When you take this orbit, this is an elliptic orbit path. This elliptic path, when Mars will come over here, so that is the orbit perigee, and this will be the apogee of this orbit, and that will coincide with the Mars here. And it was inserted here on 29/4. It was put there on this Mars. We know that's why you do not get the opportunity to put Mars to mission to Mars every now and then. It takes there is called a synodic period. That synodic period we have to know, and from there only, so at that time that this opportunity was there, and I was there, and we were in my division only. This work was also being carried, and I was also involved in this. So to some extent, so we were calculating these orbits, what kind of orbit. So we said the whatever payload we have, whatever our launch vehicle can give, it can give only a high elliptical orbit. That is perigee around 500, apogee around 80,000. If you want nearer, you should have more energy to the your vehicle, which we were not having. That's how we reach into a highly elliptic orbit. No, otherwise, ideal is there is around 100 kilometers. But I think we will be doing, the ISRO will be doing a mission to Mars, and we will come to that and maybe try to even land there. So these are the pictures taken by that Mangalyaan. This is Martian clouds as seen by Mars orbiter mission around Arsia Mons. It has got some of the where this these are all very huge ones, that is biggest in the solar system. There are these earthquakes, where this Mons earthquake, that is the longest one. And Scramjet, these are all the new technologies which India has been now trying to perfect it. First experiment mission of ISRO Scramjet towards the realization of air breathing. This was carried out on 2016, and then this was for 300 seconds, and then we had a reusable launch vehicle technology demonstrator. RLV-TD also was another thing which we have been successful. RLV-TD consists of these are the things, and many high technology machine and test equipments are utilized during the making of this vehicle. And then we have objective of RLTDs, hypersonic aerodynamic characterization of wing body, evaluation of autonomous navigation, guidance of control schemes, integrated flight management, thermal protection system evaluation. And then first test flight of RLV-TD development program was launched from Satish Dhawan 29th this 16th. So after a successful lift that lasted 91.1 seconds to a height of about 56 kilometers, the RLV-TD separated from the HS-9 booster and further descended to height of about 65 kilometers. It then began descent at about Mach 5. The vehicle's navigation, guidance, and control systems accurately steered the vehicle during this phase for a controlled descent down to the defined landing spot over the Bay of Bengal. So already they knew where it should come, at a distance of about 450 kilometers from Srirangam. The flight duration of the launch to splashdown lasted around 7 seconds. This is another new technology which our people have done. 2 stages to orbit. These are all the things which country is going to do. They are doing it, and this is this is again the reusable launch vehicle RLV. There's a lot of work already has been carried out in this area, and so thank you very much. I don't want to take more time of you.
Okay, once again, sir, thank you so much for taking out your time from your busy schedule and enlightening us with the knowledge. And thank you so much, sir. And I would like to thank our head of department, Mrs. Jalpa ma'am, for giving me permission to conduct this webinar section and inviting Dr. R.K. Sharma sir to conduct it. And I will also thank our students for paying attention and doing the work on it. Thank you so much, sir. It is a great opportunity for us and our students. They got so much of knowledge from your lecture. Thank you, sir.
Okay, thank you very much.